Hi Coach Al, this is the tutorial for using a shift register. Let's go. This is the basic code for using a shift register. So we're going to use a shift register to turn the 3 pins into 8 outputs on the Arduino board and the breadboard. So we're going to use the integer here to define 3 integers, the data pin, clock pin, and latch pin, and the pins they're connected to on the Arduino board for the shift register. And then the 74HC595, which is the shift register, is the type of serial connection called SPI, a serial peripheral interface, and that requires the data, clock, and latch pins. We're also going to declare a global variable for the data that we're sending to the shift register using byte data equals 0. Void setup, we're going to set the 3 SPI pins as outputs using the pin mode function and setting each of them to the outputs. We're going to go to void loop. And so here we have 6 different functions, and we can comment them out like this using 2 slashes to not use them. But if we want to use them, we'll delete the comments, but we can turn all of them on, all of them off, one on, one off. It all works. So these different codes, we're going to explain them down here. So before we do that, though, we're going to use the void shift right integer desired pin boolean desired state function here to it's going to let us, this function is going to let us make shift register outputs high or low here, high or low, the same way that we use the digital write function. The shift write function is going to take 2 parameters, the desired pin and the desired state. The desired pin here is the shift register output pin. You want to affect 0 to 7. Those will be the LEDs. And then the desired state here is whether you want that pin to be high or low. So it can be 1 or 0 or on or off. And so the numbers are stored in arrays of bits in the Arduino, and each bit is going to be 1 or 0 value. And a byte type is 8 bits, so we're going to use a byte in which we name data at the top, right here. Here it is. So that's going to be our byte of 8 bits. Where did we go? Here we go. And so if the bit in the byte is 1, then the output will be high, and if the bit is 0, the output will be low. And so in order to turn on the individual bits in the data on or off, we're going to use a bitrate function, which can make the individual bits a 1 or a 0. Before that, we're going to alter the global variable data by changing the desired bit to 1 or 0 using the bitrate function here. And then we're going to send that data to the shift register using the shift out function. So we're going to manipulate the data and the clock pins to move the data into the shift register here using the shift out function. And so then once the data is in the shift register, we're still going to need to make it appear. We're going to still make it appear as output. So we're going to toggle the state of the latch pin, which will signal the shift register to latch the data to the outputs, and so the latch activates on the high to low transition. So high being on and low being off. So we're going to use the digital write function here, latch pin setting it to high, and setting the latch pin to low. So here's the first function. It's function one after another. This function is going to light one LED delay for the delay time, and then light the next LED. That's going to repeat until all LEDs are on, and then it'll turn all of them off in reverse order. So first we're going to create an integer called index and an integer called delay time, and we're going to set delay time equal to 100 milliseconds to pause between the LEDs. So here we're going to use a for statement. So we're going to use a for statement to turn on all the LEDs by stepping the index from 0 to 7. Here index is going to start at 0, and if it's less than or equal to 7, the index will increase by 1 using this index plus plus. We're then going to use the shift right function and set the index to high, so that number to on, and we're going to delay for the delay time right here. And then we're going to turn all the LEDs off, so we're going to use another for statement and step backwards from 7 to 0. So when index is 7 and greater than or equal to 7, index will minus by 1, so using this index minus minus. Then we're going to use the shift right function again to set the index to low or off, turning the LED off, and then the delay for the delay time. Now, this is the second function here, one on at a time. This function is going to step through the LEDs, lighting one at a time. So again, we're creating an integer called index and an integer called delay time equal to 100 milliseconds. And then we're going to use only one for function this time to step through the LEDs from 0 to 7, again increasing by 1. We're using the shift right function again to turn the LED on by setting the index to high, delaying for the delay time that we defined right here, and then using the shift right function again to turn the index low or turning the LED off. So then the third function here is ping pong. So this function is going to step through the LEDs, lighting one at a time in both directions. It's going to go up to the 7 and all the way down again. Again, we're going to create an integer called index and an integer called delay time, setting it equal to 100 milliseconds, and the pause, it'll be the pause between the LEDs. So then we're going to step through using the for statement, step through the LEDs from 0 to 7. So we're going to step up again. So if the index is 0 or less than or equal to 7, we're going to increase by 1. Again, using the same code that we had in the second function, we're using the shift right function here is going to set the index to high, turning that LED on, delay for the delay time, and then use the shift right function again to set that index to low and turning that LED off. And then we're going to step through the LEDs down, so we're stepping from 7 to 0. So when index is 7 and greater than or equal to 0, index is going to minus 1. We're going to use the same code, so shift right and index will be set to high using the shift right function. We're going to delay for delay time again, and then we're going to use the shift right function again to set the index to low and turning the LED off. Then we get to the fourth function here, which is the random LED. The function is going to turn on random LEDs depending on a random number. So again, creating an integer called index and an integer called delay time, setting the delay time to 100 milliseconds again to pause between LEDs. And so using this index and the random function here, using this random function, we're going to set the index equal to a random number between 0 and 7 here. The random function is going to return a semi-random number each time it's called. So it's going to be between 0 and 7. And then we're going to use the shift right function again here to set that number, what the index is equal to, so the random number, to high, turning that LED on. Again, delaying for the delay time to slow down the sequence, and then using the shift right function once again to set that index number to low and turning the LED off. We get to the fifth function here, which is the marquee function. This function is going to mimic chase lights that we see on those signs, around signs and other signs like those. We're going to create another integer called index again. We're going to create another delay time, this time setting it equal to 200 milliseconds, a little longer than before. And we're going to step through the first 4 LEDs. So we're going to light up the one LED in the lower 4 and then one in the upper 4. So for index equals 0 and less than or equal to 3, index is going to increase by 1. So we're going to use the shift right function again to set that number to high, turning one of the LEDs on in the first 4 set of LEDs. And then we're going to use the shift right function again to set the index plus 4 to high. So it's going to skip 4 LEDs and set the next LED on high. So turning it on. We're going to delay for the delay time here. And then we're going to use the shift right function to set both of those, LEDs off. So the index and the index plus 4 to low and off. Okay, and then we get to the sixth function, which is binary count, which is actually right here. So the position of the byte affects the magnitude. Affects the magnitude of its contribution to the total number. And since the array of bits is equal to 1 or 0, which is similar to which is the same as the binary code, that that's how we're going to use to count in binary. We're going to build any number from 0 to 25 from the 8 bits just by selecting the contributions we need to make it. So the bits will be 1 if that contribution is used, and 0 if it is not used. So turning it on if it's used and off if it is not. So this function is going to increment the data variable from 0 to 255 and then repeat. And we're going to send this value to the shift register, and the LEDs will see an on-off pattern of the 8 bits that make up the byte. So we're going to have an integer of delay time. We're going to set it to 1000 milliseconds or 1 second. And then we're going to send the data byte to the shift register using the shift out function. So data pin, clock pin is going to send it to data here. And then we're going to toggle the latch pin here to make the data appear on the output. So using the digital write function again, setting the latch pin to high and the latch pin to low. And that's going to be the information for the outputs. And using this data plus plus function here, we're going to add 1 to data and then repeat. So just going to add up to 255. And once we reach 255, it'll go back down to 0 because the byte type can only store numbers from 0 to 255. And then we're going to delay using the delay time integer again, just so we can see what is turning on and what's going on. And that's it. Here is the basic board for using a shift resistor. So here's the shift resistor, and a shift resistor is an integrated circuit, or IC, which are small plastic sealed packages of common circuits that now they act as a single components to perform a specific job or function, and so they're now used in place of functions that used to take up a lot of space and time to build. So the shift resistor uses 8 bits of data, and if they're equal to 1, then they'll send the output, then the pin that they're connected to, that data point will be high, and if they're equal to 0, the output pin that it is connected to will be will be low. So we'll see that in the LEDs, but we'll explain it more. So in the shift resistor, you can control up to 8 outputs, and they're useful because since you can control 8 outputs, but you're only using 3 pins on the Arduino board, so that's really helpful when saving space. So how this works is that you load all the bits in first to the board, and once they're loaded in, then the latch pin can be pulled, and the LED will either turn on or off, or stay off, depending on the information that was loaded into the shift register. So on the shift register, there are three pins: the clock pin, data pin, and latch pin. And the clock pin lets the shift register lets the shift register know that you're sending a new bit, and they can move from high to low, the 0 or the 1. So then it sends that bit over to the data pin, and then that shifts the next bit into place. And so when it shifts into place, it moves to the latch pin. And so once all the bits are shifted into the latch pin and into the register, then it enables the latch pin, so it will pull the latch pin, and it will send the bits to the output pins, or the LEDs that we have here. So on the board right now, the data pin is connected through this blue wire here to pin number 2 on the Arduino board. Let's see if we can see that. There you go. And the clock pin is connected through this green wire here to pin number 3. And then the latch pin is connected through this yellow wire here to pin number 4 on the Arduino board. And then the shift register itself is, you can see here, is connected to 3.3 volts through this red cable here and this red cable here. And that's connected to the positive column, which is connected through this red wire to the 3.3 volts on the Arduino board. So that's giving it power. And then it's grounded by this gray wire here and this gray wire here, connecting to the negative columns. And this negative column is connected to the other negative column through this black wire, which is then finally grounded by this black wire here into the ground pin on the Arduino board. So then that's how the shift register works. And when we get to the Arduino, so each of these each of these LEDs are connected to the latch pin through this red or orange cable, or for the first one, this green wire here connecting to the pin up top there. And so then the data travels through these cables and wire through 100 ohm resistor for each of these LEDs into the anode of the LEDs. So setting the information to there, and then each of these are grounded by their cathodes by connecting into the negative column here, and then grounded by the same black wire here. And so then that's basically how that's working, and we can see that it's running through the different codes. So there's 6 codes running through right now, so they're all in loop, so we can see them all working. And there we go. Awesome. Here's the first function working, the step up one after another. Here's the board working for the second function, one at a time, so each of these LEDs will turn on and off. Here's the board working for the third function of ping pong. Here's the board working for the fourth function, which is the random LED. Here's the board working for the fourth function of marquee. You can see it's every fourth. Here's the board working for the binary count function, the sixth function. So we can see it's counting up, it's increasing one, and it's going back and counting each of these bits. So yeah, there we go. This is the modified code for using a shift register. So we're going to use a shift register to turn three pins into 8 or more outputs and play different notes relating to each LED using the piezo buzzer. The outputs are going to be LEDs on the Arduino board. So again, here we're going to create integers for the data clock and latch pin of the shift register. We're also going to create a constant integer for the buzzer pin using constant integer. That's going to be the piezo buzzer. Again, we're going to have byte data equals 0, or declaring a global variable for the data that we're sending to the shift register. We're going to create a constant integer called song length, and that's going to be equal to 8, which is going to be equal to the total number of notes and spaces. We're going to have the character notes equal C, D, E, F, G, A, B, C, and that's going to be the notes in the sequence. We're also going to have integer beats is going to equal 1111. That's going to be the beats of the note, so each one equals a quarter note. When we get to setup, we're going to use pin mode and set the data clock and latch pins to outputs, as well as the buzzer pin. And then we're going to set our start the serial port at 9600. So then this is the void loop. We have all of our codes right here, and we can comment them in or out using backslashes. So right now we have this one on. We'll turn on the first one on. So here we're using void shift right integer desired pin boolean desired state here. That's going to make the shift register outputs like before. And then again, we're using the global variable of data and changing the desired bit to 1 or 0 using bit right function. And we're going to use the shift out function again to shift the data from the clock pins to the shift register. And then we're going to set digital right using the digital right function, the latch pin to high and the latch pin to low. So that's going to be depending on the data. So when we get to the first code, one after another here, we're going to create an integer called index, and that's going to be the index integer, and that's going to be the number of the data here. And then we're going to create an integer I, and that's we're going to use that for the piezo buzzer. And we're going to create a delay time integer, going to equal that to 200 milliseconds to pause between LEDs. So we're going to use the for statement here. For when the index is equal to 0 and less than or equal to 7, we're going to increase the index by 1, stepping up. And so first what we're going to do is we're going to set I equal to index. So the same LED, the LED that will turn on will also play the sound relating to that LED. So we're going to use the shift right function here to set the index number to high and turning that specific LED on. We're going to use serial print here to print index equals index then index number, and then we're going to set print a space out, and then we're going to print the LED is on. We're also going to then we're going to use the tone function here to play the note relating to the LED, so the buzzer pin frequency, the note of I that I is equal to, and then delay the time. Use the serial print function again to print out a space, and then note equals, and then we're going to print out the note that is being played, and then again delay for the delay time that we specified above. Then we're going to turn all the LEDs off. So for when the index is equal to 7 or greater than or equal to 0, we're going to step down by minusing. So again, we're going to set I equal to the index. We're going to use the shift right function again to set the index to low, and that's going to turn the LED off. Again, using the serial print function here to say index is equal to the index number, printing a space and printing the LED is off. We're going to use the tone function here to play the note relating to the LED, and again using the serial print function again to print out the note equals the note being played, and then delay for the delay time that we specified above. So this is the next code, void one at a time. Just going to loop that. Again, creating an integer index, the I integer for the piezo buzzer, and the integer of delay time, and we're setting it equal to 100 milliseconds this time. So we're going to step through the LEDs from 0 to 7. So for using the for statement, index equals 0 and less than equal to 7, step up using the index plus plus. Again, setting I equal to index. Using the shift right function here, we're going to turn the LED I by setting index high. And then again, using the serial print function here to print out what the index is equal to and that the LED is on. Going to use the tone function again, so going to play the note relating to the LED and the index number. And then use serial print function again to print out what note is playing, delay for the delay time, and then print out what time we're delaying for using the serial print function. Then we're going to turn the LED off by using the shift right function to set index to low, and then use the serial print function again to print that the LED is off. Then we get to our third one here, so ping pong is our third code. Again, creating the integer index, the integer I, and integer delay time, setting it to 200 milliseconds this time. We're going to step through the LEDs again from 0 to 7 using the for statement, setting the I equal to index once again, using the shift right function to set the index to high, turning the LED on, printing out what the index is equal to and that the LED is on, using the tone function to play the note relating to that LED and to that index number, or I number, and then using the serial print function again to print out the note that is playing. We're going to delay the time using the delay time that we specified right here, serial print, and then print out the delay time again. And then we're going to use the shift right function here to turn the LED off, setting the index to low, and then print out that the LED is off. And then we're going to step through the LEDs again, but this time from 7 to 0. Again, we'll have to specify that I is equal to index, so the same LED and sound will go each time. We're going to use the shift right function to set the index to high, turning the LED on, printing that out, that what the index is equal to and the LED is on. Using the tone function again to play the note relating to the LED, printing out what note is being played using the serial print function. Delay for the delay time, print out what the delay time is equal to, and then use the shift right function again to set the index to low, turning the LED off, and then printing out that the LED is off. So we get to our next set of code, which is the random LED. Again, we're going to create the integer for index, and the integer is I for the piezo buzzer, and creating a delay time integer and equaling that to 200 milliseconds. The index is going to equal a random number. It's going to pick a random number between 0 and 7. We're going to again set the I equal to index, so the number that is the LED number that is being lit up is going to be the same as before, the same note relating to that LED. Using the shift right function, we're going to set the index to high, turning that LED on, printing out what the index is equal to and what LED is on, that the LED is turned on. Using the tone function to print out the note, to play the note using relating to the LED. Using serial print function again to print out what note is playing. Delaying for the delay time. Serial print out the time that it is waiting for and delaying for, using the shift right function once again to set the index to low and turning the LED off and printing that out as well. We get to marquee. This one's going to mimic the chase lights like the ones we see around signs. So again, we're going to create our 3 integers that we've been creating before, the index, the I, and the delay time, setting it to 200 milliseconds. We're going to step through the first 4 LEDs, so we're going to light up the one in the lower 4 and then one in the upper 4. So for when index is equal to 0 and less than or equal to 3, index is going to increase by 1. Again, setting the I equal to index. Going to use the shift right function to set the index number to high, so turning the one LED on in the first 4, printing that the LED is on, and then we're going to also use the shift right function again to set the index plus 4 to high, so it's going to skip 4 LEDs and turn the next LED on, and we're going to print that out as well. We're going to print out what the index number plus 4 is equal to, and then that LED is on. We're going to use the tone function here to play the note relating to the first LED that was played. We're going to print the note out, and then we're going to delay for delay time, print out the delay time, and then we're going to use the shift right function to turn both LEDs off, the index and the index plus 4, and then print out that both LEDs are off. When we get to our last bit of code, it's going to be the binary count. So the LEDs are going to count up to equal 255 in binary. So each LED is equal to a different bit position. So first LED is 0, 1, 2, 3, 4, 5, 6, and 7, and each of those have a different contribution. So the first LED is 1, second is 2, third is 4, fourth is 8, and so on. So you can count the LEDs and add them up to what they'll equal to. So we're going to create integer delay time is equal to 500, so that's going to be a little longer so we can see kind of what's going on. We're going to create the integer I again for the Piazza buzzer, and again set I equal to data this time instead of what we've been setting it equal to. So then we're going to send the data byte to the shift register using the shift out function, and then we're going to toggle the latch pin to make the data appear at the outputs using the digital write function. And then we're going to use data plus plus to add 1 to data and then repeat. So it's going to count up from 1, 2, 3, 4, 5, all the way up to 255, and then start over. So first what we're going to do is going to print out data equals data. So it's going to print out what the number that data is equal to from 1 to 255. And then we're going to use this set of else, if and else statements here to figure out what note to play. So this function here says if I is divided by 128, the remainder is 0. So that means that it divides evenly by 128. If it divides evenly by 128, that means that the last LED that is turned on was the LED relating to the bit position that contributes the 128 number to the total number. So the bit position will be 7. And that the last LED will light up, and that tone will play. But if the remainder does not equal 0, that means it doesn't evenly divide into the number. It'll go to the next statement here. So before we get to that, the tone, we're going to use the tone. If it does evenly divide by 128, then we're going to use the tone function to play the note relating to that LED, and we're going to use the serial print function to print out the note. Note 7, the 7th number in the note sequence. So else if that is wrong, we're going to go to the next statement here. So if it's divisible by 64 and there's no remainder, then the next note will play because that's going to be the different LED that's the last one lit up. I'm going to print that out when the note is playing again, and we're going to continue that down that same formula all the way down to the last possibility that is divisible by 1. We count down from 128, 64, 32, 16, 8, 4, 2, 1 because everything's going to be divisible by 1, but the further we go up, if it can be evenly divisible by the largest number, that's going to be the last one that's going to be lit up. So whatever LED is flashed on last, the note will play. I'm going to print out each of the notes that if they're played. And then we're going to delay for the delay time. Here we have the code that's going to say what note is equal to what frequency for each character note. So integer I here, creating an integer for the piezo buzzer. We're going to create a constant integer of num notes is going to equal 8, so that's the number of notes we're going to be storing. And so then these arrays, the chart names, so that's going to be the character names, so C, D, E, F, G, A, B, and uppercase C. And then the integer frequencies are they're going to be relating to the notes. So 262 is the frequency for C, 294 for D, 330 for E, 349 for F, 392 for G, 440 for A, 494 for B, and 523 for uppercase C. And then we're going to use a for statement here. So we're going to search for the letters in the right, and if we find it, then we will return the frequency to that note. So for when I is equal to 0 and I is less than the number of notes, we're going to step through the notes. If the name equals the note, then we're going to use the return function here, the frequency to send that specific frequency to the buzzer. And if we look through everything and we can't find it, we're going to use the return function again and return the value of 0, so no note will play. And then that's it until we get to the serial monitor. This is the serial monitor for the code of one after another. You can see it's working. This is the serial monitor for code one on at a time. So here we go. This is the serial monitor for the ping pong code. This is the serial monitor for the random LED code. So we can see it's different notes every time. This is the serial monitor for the marquee code. So we can see that all the LEDs are turning on and different notes are being played and delay time. This is the serial monitor for the binary count. So we can see that the binary is counting up and each note is being played. Here's the modified board for using a shift register. Everything's the same except for the piezo buzzer is now attached here. It is grounded by this black wire here that is connecting to the negative column on the board. That's grounded by the black wire again over here. And then it's connected to pin number 6 on the board. Pin number 9 on the board through this yellow wire here, which connects to its positive side. Yep, and then that's it. Here's the board working for the one after another code. Here's the board working for the one on at a time code. Here's the board working for the ping pong code. This is the board working for the random LED code. Here's the board working for the marquee code. Here's the board working for the binary count code. So the last LED that turns on plays the sound. And it's count up. And it'll go all the way up to 255, but it takes a while. So yeah.